Hi all, this is going to be a lecture series on numerical in algebra. In this video, we are going to see review about the mathematics of eigenvalues and eigenvectors. The algorithms to compute eigenvalues and eigenvectors will be discussed in the later part of the lecture series. So, consider the equations 24.1 ax equal to lambda x. A is a square matrix. The vector x which satisfies this equation is termed to be as an eigenvector, and lambda is an eigenvalue. A set of all vectors which satisfies this equation forms an eigenspace, and the element in that eigenspace is termed to be as an eigenvector. And similarly, a set of all values which satisfies this equation is termed to be lambda values which satisfies this equation termed to be as eigenvalues, and the set of eigenvalues are termed to be as a spectrum of E. So eigenvalue problems like equations is similar to like kind of a linear system of equation that we saw earlier, ax equal to b, but there is a fundamental difference. In linear system of equations, the domain of A not necessary to be same as the range of A. But in respective of the equation 24.1, the eigenvalue problems, the range and domain space are the same. So using this property, mostly the eigenvalue problems are utilized where the matrix has to be compounded iteratively. For example, to compute the power of A raised to value k, or it necessary to compute a functional form where A is involved like exponential to the power of A. And these eigenvalues and these systems are mainly utilized in two perspectives. One is algorithmic perspective and another is analyzing the real physical systems. In algorithmic perspective, where we have a nonlinear coupled equations, it helps us to formulate decoupled scalar problems. With respect to analyzing the physical systems, it helps us to understand the dynamics of the physical systems, how it evolves, whether it's stable, or how about the fixed points when it evolves in a large number of time steps. So these are the main applications for analyzing the eigenvalues and eigen vectors for a particular system of equations. So next, the thing definitions comes here is eigenvalue decomposition. It's a matrix factorizations. Whenever the matrix is factored in a form in respect to 24.2, a diagonalized form, then it's termed to be an eigenvalue decompositions, provided that X is a non-singular matrix. So in a matrix format, this is written as like this. For example, when we take in the jth column, then it will be entered up in a eigenvalue equation similar to what we saw earlier in 24.1. Lambda j is an eigenvalue and xj is an eigenvector. And geometric multiplicity is kind of a definitions. For example, a set of eigenvectors and the number of eigenvectors corresponding to a singular eigenvalue is termed to be as a geometric multiplicity. So it is something like a maximum number of linearly independent eigenvectors for an eigenspace, where that eigenspace is found for a particular eigenvalue. So characteristic polynomial is defined by equation 24.5, and the roots of these characteristic equations are termed to be as an eigenvalues. So that's what the theorem 24.1 says. So lambda is an eigenvalue of A only if it is roots of a characteristic polynomial defined by equation 24.5. And one of the thing is, even though the eigenvalue systems are assumed to be a real system, physical system, but the eigenvalues not necessary to be as a real, it can be a complex, which means that it can be in the systems not necessary to translate from one point to another point. It can also be an oscillatory behavior. That is what it shows, that the complexity of the eigenvalues. So what is meant by algebraic multiplicity? Similar to like kind of geometric multiplicity, and eigenvalues where it appears here in the characteristic polynomial not necessarily to be distinct. If this if the same eigenvalue appears more than once, then it's termed to be as an algebraic multiplicity for that particular eigenvalues. So if in case if an eigenvalue is only appears once, that means it means that the algebraic multiplicity is only one, then it's the eigenvalue is termed to be as a simple eigenvalues. So if If the system is the roots of the systems are simple, it means that it has m distinct eigenvalues. Obviously, so another important characteristic of this system is algebraic multiplicity of an eigenvalue is always at least as great as its geometric multiplicity. The next important thing here to be considered here is a similarity transformations. A matrix which gone through this transformation is called a similarity transformations, provided that x is a non-singular value. And let us consider this transformed matrix to be as a B, and A and B are similar. If A and B, that if it is gone for a similarity transformations, then the theorem 24.3 is what it says is the characteristic polynomial eigenvalues and algebraic multiplicity appear to be are the same. So we are not going to go into the analysis of the proof. So another theorem here what says in this chapter is algebraic multiplicity of an eigenvalues at least as great as is geometric multiplicity. So that we already saw before. So defective value eigenvalues and defective eigenmatrices. What does mean by that? So eigenvalues whose algebraic multiplicity exceeds its geometric multiplicity is termed to be a defective matrix, defective eigenvalue, and whichever the matrix has defective eigenvalue is termed to be as a defective matrix. And a very important property is whenever a matrix is diagonalizable, then it's a non-defective. There won't be defective eigenvalues and not necessary to be as a defective matrix, and it's termed to be a diagonalizable diagonal matrix is termed to be as a non-defective matrix. So that's what it says in this theorem. Matrix is non-defective and only if it is having a diagonalizable form. It is an eigenvalue decompositions that we saw earlier. So how would be the behavior if it is a diagonalizable matrix? So if a matrix is a diagonalizable, how correlate the behavior of that diagonalized matrix whether the behavior would be same, it depends upon the condition number of the x. If the condition number is very L condition, then the property what it contains in the matrix A would be lost when it is transferred to that diagonalizable matrix. But if it's in well condition, then both behavior would be appear more or less would have a similar behavior. So determinant of a matrix can be computed from the eigenvalues, and trace of the matrix also can be computed from the eigenvalues using the equations. 24.8 can be computed by the product of the eigenvalues. It can be computed from the sum of the eigenvalues. Then the second factorization. The first factorization is an eigenvalue decomposition. The second factorization, what we are considering here, is an unitary diagonalization. So before we saw that it can be a diagonalizable if provided that X is a non-defective matrix. Here what here is, and X is having additional property that X is not a normal matrix. So this transformation can occur only if matrix is matrix A is a normal matrix. So or a Hermitian matrix or a normal matrix. So only a Hermitian or normal matrix has this kind of transformations or unitary diagonalization transformations. So that's what it says in theorem 24.8. A matrix is unitary diagonalizable if and only if it is a normal matrix. The third kind of factorization is a skew factorizations, and it's a very important factorization is a unitary triangulations. And it one of the important key uh, characteristic of this transformation, any matrix, whether it is a defective or non-defective, whether it's a normal or non-normal, can have a skew decompositions, and where there will be a unitary triangulations, and the triangular matrix will have the eigenvalues along this diagonal elements. So this is what says in theorem 24.9. Every square matrix has a skew decompositions. So in this lecture, we have seen three form of factorizations to compute eigenvalues. First one is diagonalizations, that is called as eigenvalue decomposition. If this kind of factorization exists only if A is a non-defective matrix. Second one is important specialized transformations or specialized factorization called unitary diagonalizations. If that this can exist only if matrix A is normal. Third one is unitary triangulations. Then this factorization can exist for any matrix, not necessary to be as a non-defective or a normal matrix. So once we most likely we eigenvalues are computed using the third kind, which doesn't have any particular conditions for the matrix to be satisfied. And moreover, since it's an unitary transformations and the algorithms to compute this eigenvalues using skew factorizations are mostly numerically stable. Hopefully we'll see about details about the way we wanted the algorithmic setup to compute eigenvalues in the next lecture. Thank you.